Hello everyone, welcome to this channel. So our question says the statement among the following that is a tautology is, and there are four different statements given. So when you see such, by the way, these kind of questions are very common in JEE Main. So when you see these kind of questions, these type of questions could be solved in multiple ways. So one approach is using truth tables, another way is using laws or identities from mathematical logic. Another approach is using the equivalence using set theory, so by just drawing Venn diagrams. Another approach is just by actually understanding what the statement means by taking an example or something like that. So there are multiple approaches to solve such a kind of question, but of course for some questions using truth table will be the easier approach. For some question using Venn diagrams will be the easier approach, so that you should be able to choose during an exam. Anyway, I'm going to tell you all the ways in which you can analyze each and every option given in the question. Okay, so at the end of it, you will be able to realize that this question can be done within a minute if you have very good grasp of the concepts that I'm going to discuss right now. So this is going to be a thorough analysis of all the statements and how it can be analyzed using different approaches. So make sure that you go through the entire video because you will be learning a lot of things, and in the end you will realize that if you know all these concepts, you will be able to do this question in a minute. So let us take the first statement. It says A or A and B. Okay, we have to check whether it is a tautology or not. Okay, so the first approach is by constructing a truth table. So let us construct a truth table. So in the truth table, we need to have A, we need to have a column for B, we need to have a column for A and B, and we need to have a column for A or A and B. So let's take all possible combinations: TT, TF, FT, FF. A and B is going to be T here, F, F, F. Now we have to take OR with the first column and the third column. So this is going to be T, this is going to be T, this is going to be F, and this is going to be F. And it is not a tautology. If it were a tautology, you should get straight T's everywhere for every row. And do you observe that our first column and the last column are exactly the same? So this means that A or A and B is logically equivalent to A. Okay. Now let's see the second approach. So here I'm going to prove that A or A and B is equivalent to A using the laws or the identities that we have learned from mathematical logic. Okay, the first thing that strikes our mind is the distributive law, which says that A or B and C is equal to A or B and A or C. Basically, this means that OR is distributive over AND. Okay, so let's apply that here. So when I apply it here, we have A or A and A or B. Now A or A is equal to A. This is what we call an idempotent law. So your LHS, we started with our LHS. So our LHS becomes A and A or B. Now at this stage you're stuck because our current expression looks similar to the one we started with. So if you apply distributive property once again, we are going to go back to the say if I distribute the property again, we have A and A or A and B. Now you are stuck with you're coming back to the original question. So you are coming back to the original question. Yes. And in fact, this expression happens to be the one that is given in option number 2, right? So this is a little bit tricky. Okay. So we can't follow this approach. So what I'm going to do is I'm going to do take a little tricky approach here. So we have to start with A or A and B. And what I'm going to do is I am going to rewrite A as A and T. All right. A is written as A and T. A is written as A and T. So A and T is equal to A. This is what we call an identity law. Identity law. Now we can apply the distributive property here. So this becomes A and T or B. T or B. Now what is T or B? T or B is same as T or B is same as B or T, and it is called the commutative law. So this is A and B or T. And now what is B or T? So B or T is nothing but T. And this is what we call a domination law. Domination law. B or T is equal to T. So that is domination law. And so we have A and T. Now what is A and T? A and T is again A using the identity law. So we have A. So we have seen several laws from mathematical logic here. So this was a little tricky one, but we have arrived at the answer. Now, the third approach is using Venn diagram. Third approach is using Venn diagram. So we have to consider the equivalent statement from set theory. So in the set theory, this would be considered as equivalent to A union A intersection B. So instead of mathematical statement, you consider sets, and this is a universal set. So we have A here and B here. This is A, this is B. Now this is your A and B region, this region, and that is union with A. So we have A here. So if you take union of these two, what you're going to get is again A, right? Let's see the next approach now. So we had a truth table approach. This was number 1, and this was number 2 using the identities from mathematical logic, and third one was using Venn diagrams. In the fourth one, I'm just going to use our intuition. So we have to figure out what this means, A or A and B means. So let's say I'll consider statement A, I have a burger. B stands for I have cheese. Now, what does this stand for? A or A and B. So this is equivalent to I have a burger or I have a burger and cheese. Now think about this statement. It says I have a burger or I have a burger and cheese. Maybe say I have a cheeseburger. So when you combine these two statements, it simply means that I have a burger. So this is equivalent to saying this is equivalent to statement A. So that is the fourth approach of doing this question. Now, if you take the option B is similar to this part. It can be done in 4 of these methods. So I leave it as an exercise to you. So these two parts are together known as absorption identities or absorption laws. So those of you have studied this as absorption laws, you will be able to realize that, see, even if it is from set theory, if you have encountered these results previously, you will be able to eliminate these two options because these two are not tautologies. Now let's go to option number 3. Okay, third option. So option 3 talks about B implies A and A implies B. So the first thing that comes to our mind is using truth tables. So we can do that using truth table. So we can draw a truth table for, there is a column for A, there is a column for B, there is a column for A implies B, there is a column for A and A implies B, and there's a column for B implies A and A implies B. Now there are 4 combinations: TT, TF, FT, and FF. Now, what is A implies B? A implies will be false when A is true and B is false. So you can imagine this as a fulfillment of a promise. For example, if I say, if there is an elephant in the library, I will give you 100 rupees. So if A is true and B is true, suppose there is an elephant in the library and I give you 100 rupees. So the statement is true because the promise is fulfilled. Now, if there is an elephant in the library, I'm not giving you 100 rupees, then the promise is broken, then it is false. Now, if there is no elephant in the library, even if I give you 100 rupees or if I do not give you 100 rupees, does not matter, because the statement doesn't talk about what happens if there's no elephant in the library. So if there's no elephant in the library and I'm not giving you 100 rupees, then also the statement is still true because the promise is not broken. And if there is no elephant in the library and if I still give you 100 rupees, you can say that when you're fulfilling a promise, you can be generous. Okay, so this case is also taken as true. So remember this truth table. For A implies B, the statement becomes false only when there is an elephant in the library and you are not giving money. So that is cheating, right? Now let's see A and A implies B. So we have to take and with the first column and third column. So this is T, this is F, this is F, and this is F. Now we have to take B implies to this. So elephant and money, true. No elephant, no money, that is true. There is elephant and then there is no money, then that is F. And there is no elephant, there is no money, then that is true. Now, do you observe that this TTFT corresponds to actually B implies A? This corresponds to B implies A. Why? Because if you take B implies A, see, this will be T, this will be T, and the third case, there is an elephant, I'm not giving you money, so it is F, and this is T. So these two are exactly the same, and this is just observation. Okay, this is pure observation. Now we have seen that B implies A and A implies B is equivalent to B implies A using truth tables. Okay, so that is one approach. And in the second approach, you can use the algebra. So in the second approach, so this was our first approach for the option number 3. In the second approach, what I'm going to do is I'm going to use the algebra, the laws of mathematical logic. So we have B implies A and A implies B to begin with. Now you have to remember this. A implies B is equivalent to negation A or B. This can be proved using truth tables again, or even using Venn diagrams. So you have to remember this equivalent statement. So in this case, this is going to be negation B or A and A implies B. So this is equivalent to negation B or A and negation A or B. So this is negation B or A and negation A. I'm using distributive property here, or A and B. So this is negation B or A and negation A. A and negation A is going to be always going to be a contradiction. A and negation, this is what we call negation law. So A and negation A is going to be contradiction. It is always false. So C or A and B. Okay. Now C or with anything. C or with anything is going to give you that quantity. Okay. So this is negation B or with A and B. All right. So what we just saw is C or with some statement, say X is equivalent to X. And this is one of the identity rules, identity laws. Okay. Now again, use distributive property, negation B or A and negation B or B. So this is going to be negation B or A, and this negation B or B is going to be T. Again, this is one of the negation laws. So this is going to be T. Now this something X and T. X and T is going to be X, and this is one of the identity laws. So this is going to be negation B or A, and this is equivalent to B implies A. So this is second way of proving it using the laws of mathematical logic using equivalent statements. Okay. Now there is a more intuitive way to prove this, and this approach is what we call hypothetical syllogism. So our third method is hypothetical syllogism. Okay, I'll just explain it in detail, so don't get scared by the name. So it's a very simple idea. So if I have P implies Q and Q implies R, therefore you can write that P implies R. This is a very simple idea, right? For example, I'll take an example. So let's say P is the statement, it is raining today. And Q is the statement, we will not have a barbecue today. R is the statement, we will have a barbecue tomorrow. Now suppose if we have P implies Q, so it means it is raining, implies we will not have a barbecue today. So if it rains today, P implies Q is equivalent to saying if it rains today, we will not have a barbecue today. Now Q implies R is equivalent to saying if we do not have a barbecue today, then we will have a barbecue tomorrow. Now, if both these statements are given, then you can simply write P implies R. Therefore, P implies R. Why? Because therefore you can say that if it rains today, then we will have a barbecue tomorrow. So that is the simple idea of rule of inference, what we call as hypothetical syllogism. Okay, so to use this, I am going to give you another piece of information. Now, as you know that A implies B in terms of set theory, this is equivalent to negation A or B. Okay, or you can say that this is equivalent to A minus B the whole complement. A minus B whole complement is the equivalent statement. Right. Now, if A is a subset of B, what happens? If A happens to be a subset of B, what happens? A minus B becomes null set and your A minus B complement becomes the universal set. So what it means that if A is a subset of B, the corresponding statement from logic A implies B is going to be a tautology. This is going to be a tautology, right? Now, you also know that this expression A and A implies B will be A and A minus B the whole complement. So if you draw a Venn diagram, so this is going to be A, this is going to be B, and your A minus B whole complement is going to be this area, this part. Now you take intersection with A, so this is your A. Okay, so this is our required region. So this region, so this is going to be, this is equivalent to A and B. Now since A and B is a subset of A, since A intersection B is a subset of A and B implies A. It's a tautology, right? So when it is given that B implies A and A implies B, and you also have A and A implies B. So this is given. Okay, this implies A. This is because this is a tautology. This is true. Now, just using the rule we just discussed, the hypothetical syllogism, we know that this is equivalent to saying B implies A. Okay, so I request you to go through this discussion once again so that you understand that you are very clear with the logic. Okay, now that is about the third part. So third part is equivalent to B implies A. So what is given in the third option? B implies something which is a subset of A. Since that quantity implies A is a tautology, we know that B implies A, and this rule of inference is what we call hypothetical syllogism, right? Now we have option number 4. So in the fourth option, we have A and A implies B implies B. So basically, it's the converse of statement number 3. I mean, option number 3. Let's see what that means. Now, option number 4 is A and A implies B implies B. Okay. So one method is to do it using truth tables. So let's see the truth table. We have already drawn the truth table for the converse. Right. Now let's just add one more column here. Just add one more column here. B implies A and A implies B. Okay. So B implies, no, I think, I'm sorry. It has to be the other way around. So we need to have A and A implies B implies B. So let's see how this can be done. So this implies this. Again, T implies T is T. F implies F is T. F implies T is T. F implies F is T. See, you see that that is a tautology. So from truth table, this is a tautology. Okay, that is one approach. And the second approach is, again, you know that this A and A implies B can be simplified as A and B. We just saw that. So now this is A and B implies B, right? Now let's again apply the equivalent statement for A implies B. So this is going to be negation of A and B or B. Now apply De Morgan's law. So this is equivalent to negation A or negation B or B. Now you can use negation A or negation B or B. This is what we call the association law, associative property. Now negation B or B is going to be T. So this is negation A or T. Negation A or T is going to be T. So using the properties, the laws of mathematical logic, we have obtained that this is a tautology. So that is the second approach. And the third approach is by using a technique what we are going to call as Modus ponens. Modus ponens. Okay, don't get scared by the name. It's a very simple idea. The idea is very simple. So if I have two statements P, another statement says P implies Q, therefore you can write Q. I'll show you a simple example to understand what is happening here. So consider the statement P you have the current state, you have the current password. Okay, Q is you can log on to the network. Now suppose two statements are given. So you have the current password, okay, and also the second statement says P implies Q. So if you have the current password, then you can log onto the network. Now think about these two. So there are two statements given. You have the current password, and the second statement says if you have the current password, then you can log onto the network. So therefore you can say that you can log onto the network. Yes. So if we have P and if we also have P implies Q, therefore we can write Q. So that is the simple idea. Okay. So this can be written as a tautology as P and P implies Q implies Q. Okay. If truth of P and truth of P implies Q are given, then it leads to the truth of Q. Okay. So this is this rule of inference is what we call as modus ponens. Okay. This is always a tautology. Always a tautology. So that is another approach. So when you look at the options, the answer is the fourth one. Okay, this is the right answer. So when you look at the question now, since we have gone through all of this, we can see that this is a very simple question if you have good idea of what we have discussed in the class. So first two are nothing but the absorption laws. So this is equivalent to A. This is equivalent to A. Now this using hypothetical syllogism, you can write that this is equivalent to B implies A. Now the fourth one using modus ponens, you can write that this is a tautology. So if you have these ideas, you can simply do it in maybe say 30 seconds or 1 minute. So I request you to go through this video once again, and we'll catch you in a new video soon.